Hi, I'm Leandro Facchinetti, and let's write some code together, shall we? What we have on the menu today is noise. We are going to continue working on our JS Effects library, this library that is going to help you develop better looking and easier to develop, hopefully, real-time audio processors for Reaper. And let's hear and implement and look at 3 different kinds of noises today. We're going to start with probably the one that most people know about, and it's arguably the most useful and the most common one, white noise. And I already have a video about this way back in the channel, so I'm going to just briefly go over white noise. Then we will dive into brown noise, which is a different kind of noise, and then pink noise. And we are going to implement all 3 of them for our library. So I'm going to start by changing the output, and this time we will want to hear some of the effects. So I'm going to go to the computer sounds output. That goes to me as well as to you. And how about we start with white noise, and we can first look at white noise. I actually did not open the Wikipedia article for this one. So here it is, the Wikipedia article for this one. And this is what white noise looks like when you plot it on an oscilloscope. The waveform has no shape to it. It's just jumping up and down like crazy. And there is no spectrum analyzer here to see the waveform, to see the frequencies. But we can quickly come here. I'm going to mute the master. We don't want to hear all these noises right away. So Reaper comes with a white noise generator, and I have a couple of my own. Let's look at the white noise in the oscilloscope. And as you would expect, there is no shape to this, just random samples going up and down. And let's look at this in the spectrum analyzer. And I will have to change a setting that will make more sense in a moment. But this is what white noise looks like in terms of frequencies. It's almost a flat line. It should be a flat line. It is a flat line. So that means that there is a little bit of sound on each frequency. And there is a video in which I go, as I mentioned, there is an old video in my channel in which I talk about white noise, and I explain all of this in a lot more detail. But the essence is that if you look at this, can I move the cursor this way? No, I can only move the cursor that way. Okay, so the essence of why white noise does what it do, which is to have a flat frequency response and to have a little bit of sound on each frequency. The way that works is that, for instance, look at these 2 samples. This is a relatively low frequency, or it's a slice of a relatively low frequency sound wave. Then look at these 2. They change a lot. So this is a slice of a high frequency wave, and this is somewhere in between. This again is a high frequency one. This is a low frequency one, relatively. And this is a relatively higher frequency. So adding all of this together, you have slices of low frequency sound waves, high frequency sound waves, everything in between, all put together. That's why white noise looks like this and looks like this in the spectrum analyzer. So this is the implementation of white noise that comes with Reaper. How about we replace this with our own implementation? Let's dive into our library. And think about where we want to put this. Definitely before the design system, but let's put everything else that is related to digital signal processing. And for whatever reason, I forgot to capitalize this, so I'm going to take the opportunity to do that. Noises. So noise white is going to be a function. And most of you probably know that white noise is just picking random values. There is no order to the samples that we looked at here in the oscilloscope. So just take a random value. There is a wrinkle. This is a function that comes with JS effects. It returns a random value, but it's a random value between 0 and 1. And our samples must be between -1 and 1. So to fix that, we can multiply by 2 and subtract 1. Think about the ranges. This goes from 0 to 1. This goes from 0 to 2. This goes from -1 to 1. So this is generating white noise at full scale, going from -1 to 1. Let's have a page in the demonstration effect. Oh, I actually think that to make all of this work, I need to drag this into a different folder. So hang in there while I do this, because I was working on the folder that is not the folder that Reaper is going to pick up. So I have to do a little bit of maintenance here. I think it's safe for me to just get rid of those guys. But because I am not 100% sure, I'm going to just have a to-do folder here for my future self. So with that out of the way, let's do that little bit of maintenance. I need to drag these two into there. And I do need that doesn't look right, does it? No, it does look right. Okay, that looks good. And then the other one is the demonstration effect. No, not that one. Okay. All right. All right, here we are. We have our white noise generation function here. Let's have a page for noises. I think I'm gonna put this somewhere. Doesn't really matter all that much. I'm going to put it as the first page so that when we are iterating on this code, it's easier to do it. So noises. And then we'll have a page for noises. And then I need to switch all the pages one off. So how about I do it like this? Great. So now when I go into Reaper and I load I'm going to load our effect. It is called demonstration. And we are on the noises page. It's not producing any noise right now. Great. Then let me commit this. and go to the sample block, where we'll check if we are on the page, and if we are, then let's produce some white noise. I think I want a couple of sliders for this. Yeah, let's do it. So I will have slider 13, slider noises type. It is going to start with 0. It's going to go from 0 to 2 in steps of 1, and the choices are going to be white, pink, and brown. And I'll also have a gain that will start at minus, let's say, 60. It's going to go from minus 60 up to 12 in steps of 1. And I'll call this the gain in dB. Then I need to hide these sliders so they only show up when I am in that page. So I'll go real quick to the slider block, and I will make it so that the sliders show for this slider. In other words, I'm only going to show this slider if the slider page is the noises one. Similarly for the gain. Cool. So now check this out. I'm going to remove and re-add our effect, and then it doesn't work. Great. And the complaint is in line 344. Okay, the problem is that we have an empty block. But I'll just put something there, then it will stop complaining. It's still showing, okay, so yeah, if I switch to another page, then those sliders go away, but if I am on this page, then the slider shows. So in this case, I have a white noise at minus 60, and then I can slide. Of course, I'm still not generating any sound, so let's go in there and replace this 0 with, I'm gonna do different white noises for all the different channels. It's gonna be a multi-channel kind of thing. So I'll do similar trick to what I'm doing here. And I'm gonna say that the sample on the sample channel is equal to a call to this function. Okay, so there is some sound coming through, but I don't see it because it's in the wrong order. Okay, and this is not respecting the gain. It's always at gain 0 because I made the thing go from -1 to 1. So let's actually respect the gain by multiplying by, well, actually I have to do a bit more. I have to check what is the type of noise that I have going on. So I have white is 0, and then pink and brown. And then I can check if my type is equal to white. Only in that case, I am going to run the block that does white noise generation. Great. And I'm going to have similar blocks for the other colors. So let me just get that out of the way. And I will put zeros here so I don't get that kind of weird error. Or maybe I'll have a to do here so I don't get that kind of weird error with empty blocks. Great. So now I'm doing this, but this is, again, just putting the thing in full scale. So what I'm going to do is, after this is over, or maybe I'll have a variable for this, right? That could be nice. So I'll have a sample noise equals to that. So just a local variable. And then I will do SPL at the sample channel is equal to the sample noise times, this is in dB. So I will have a variable in the slider block to convert this. Let's go to the slider block real quick. And I will have, as far as I remember, this is the only case in which I was using this variable. All right. Is equal to a call to our function that converts from amplitude to dB. dB to amplitude, actually. That's what I want. Currently have the value in dB. And I want its amplitude. Then that is going to be what I end up using here. Okay, so let's check if this is going to work. What I expect to happen is that I will drop this effect here, and it is generating white noise at -60. Then I increase the gain, and it's generating white noise at louder values. And -60 is actually kind of a special value. I want this -60 to be -infinity. I want you to load the effect in such a way that it's not going to make a noise, and then you can slide it up. So I am going to find the place where I'm doing this amplitude to dB conversion, actually, and I will check if my slider dB is equal to -60, or even less than or equal to -60, because you may be able to just come in here and type in your own values. So in that case, I want the amplitude to be 0. Otherwise, I will actually do the conversion. So this way, I'm special casing this -60 to be -infinity dB or 0 amplitude. So let's quickly check what this looks like. It should not be producing any audio, and then when I go to 59, it should start producing audio, and it's not. So let's see what that's about. Oh, forgot a minus in there. Yep, great. So there you go. That's white noise. That's why it works. It is this thing that contains slices of audio forms, audio waves in all the different frequencies. And we were able to reproduce here a behavior that pretty much resembles the one that happened in the default stock white noise generation in REAPER. Except that our version is multi-channel. So if you wanted to generate 6 channels of white noise, now you can. Let's commit this and move on to brown noise. And you may notice that I said I was going to do white, pink, and brown, and I'm going from white to brown. Yeah, we are going to do pink later because pink is actually probably the most difficult to do. Right, so brown noise. First of all, it's not brown because of the color. It is brown because of the person. The person being Robert Brown. And if you were to think about it in terms of colors, oh, hey, Bo. Bo is here. Hello. Great to have you here. And you missed the first bit, yes, but you didn't miss a lot because I was mostly recapping something that you probably already know. White noise is just random samples, and if you look at it in the frequency spectrum analyzer, it looks like a flat line. Of course, there is a lot of noise here. Noise. Well, there is a lot of variation. But if you can integrate that over time, I'm not sure I can do that with this frequency analyzer. But if you integrate that over time, it's going to resemble a flat line. And it works like that because there are slices of variations that are small, so low frequency variations, and there are slices of bigger jumps, so higher frequencies variations. And like, look at this one, it goes from here to there. So that's a big variation, very high frequency. So it contains slices of waveforms from different frequencies. And that's why white noise does what it does. Oh, and I guess I should show what it sounds like. So yeah, let's hear a bit of white noise for a moment, but some quiet white noise preferably. So let me unmute the master, then bring this up. Oh, I also need to bring this up. And that's some good white noise right there. So next, let's talk about brown noise from this guy, Robert Brown. He documented the phenomenon in physics that is like a particle like dust on water moves around, and it is erratic and it's a bit random. It eventually gets somewhere. Yeah, and Bo says that he uses white noise all the time to test his coding. And yes, white noise is useful because if you are doing something like a filter, then you can just feed the filter some white noise. You know that the white noise is going to be almost like a flat line. So if your filter is doing a low cut, you'll see all these low frequencies going away, for instance. So yeah, it's a very good testing noise to use. Now let's talk about brown noise. Why does it have that name? Well, because of the guy. And what is the relationship between particles on water and brown noise? If you think about it, if you think about noise in terms of light, white noise is called white noise because it resembles white light in the sense that it has all the frequencies. And brown is the name of the guy. But if you think about it in terms of color, it's more like red noise because it contains more low frequencies. This is the spectrum of brown noise, more low frequencies and less of high frequencies. So some people use the term brown noise, some people use the term red noise. And how do you generate brown noise? That's the key. That's where the relationship comes from. The particle moving on water moves randomly, but it doesn't jump around. The particle is here and there, it's there, and then it's in that other place. No, it is floating on water and it's moving around, and that movement is random, but it is based on the position of any given time is kind of based on Ari is here, law, Wiener process. Yeah. So the position of the particle over time is random because there is some random movement happening. But that position is not random like white noise is random because it's not jumping around all over the place. No, it is here and then it's moving randomly somewhere and it's getting somewhere and then getting back, that sort of thing. So that's where the relationship is. What we are going to do is we are going to, I don't think there is a visualization for this over here, but there is this excellent article by Martin Gardner from, I guess, 1977 or 1978 on Scientific American. And he describes the techniques we are going to use to generate these kinds of noises. And there's a lot of philosophy and physics and fractals, all that sort of fun stuff. But we are only interested in the noise part of the paper right now, or the article. In any case, you can see this is the waveform for white noise. It's just completely random, jumping up and down. But Brownian noise, it resembles the movement of a particle on water, doesn't it? Each sample is moving around randomly. Sometimes it's going to go up or it's going to go down. But it is based on the previous sample. It's movement based on the previous sample. Cool. And how do we know if you get there? Well, with white noise, it was kind of simple to know that we got there because we have had a flat line. And with Brownian noise, or with brown noise, we'll know that we got there if we see a line like this that is not straight but has an angle, and that angle needs to be 6 dB per octave. Now, we could look at this graph and see if we have 6 dB per octave. But I'm using this spectral analyzer because it comes with a convenient feature called a tilt. So I can tell the whole analyzer to tilt by 6 dB. And now what was a flat line is now a line with an angle of 6 dB. And this is a positive angle. So now this is white noise with a 6 dB tilt. And we will know that we succeeded to create Brownian noise if we turn this into a straight line. Right, so let's write the code for this. And we could, in theory, try to come up with some EQ curve that had a tilt to it and then create white noise and filter it. And I'm not sure people do that for brown noise. I'm pretty sure that people do that for pink noise. We are about to see that. But we are not going to do that. We are going to simulate this physical interpretation. We are going to have some value. It may start at 0 like this one does. It doesn't really matter. And then we are going to go up and down randomly, but not by choosing random samples. We are going to choose a random amount to go either up or down. And we are going to keep things simple. We want to be in the range of between -1 and 1. So what we are going to do is, if we go over 1, we are going to wrap it around. And if we go below -1, we are going to wrap it around. Now, this is not strictly speaking the thing that you should do. What you should be doing instead is filtering, so you don't go above or below. But it's such a small detail that I don't think it matters at all. I think it sounds about the same. Now, if you were doing noise for calibrating equipment or for some medical imaging sort of thing, then probably that wouldn't fly. But for our simple purpose of just helping someone on a mix and they want to calibrate some sort of hardware, and yeah, it should be good enough. All right, so let's try to make this a straight line. Let's go to starting with the library, I guess. Yeah, we can start with the library. We can either start with the library and do the implementation, or we can start with the demonstration and try to use the implementation. But there is something to be aware of. Bo is asking, so it's basically a low-pass smoothing. Well, sort of. It's not a low pass in the sense that there will be a pass band and a reject band. It's more of a tilt sort of thing. So if you may think of a tilt EQ kind of thing, but it's not a low pass. Usually a low pass has a pass band, a reject band. That's not what is happening. Right, so there is something that in white noise, we don't have to remember previous samples. There is no notion of memory because we are always creating something completely random and unrelated to previous samples. But in this case, for the Brownian noise, we do have to remember our previous sample because we are doing an increment or decrement based on that. So I will create a data structure to remember the previous sample, much in the same way that we had data structures to remember previous samples for our filters. So How about I borrow some of this logic? And Bobs and Y is here. Hello, let me catch up. Hello, Bobs. Great to have you here. Hope you enjoyed the ride. We are doing noise today. So I'm going to create a function called noise init, and I must remember to call this function. I made this mistake before and it was devastating. So this function must be called on the init right about here. This is the block that runs when you are initializing the code and you call the initialization of the library. So there you go. And we are going to create a data structure. It's not going to be named like this, but it's going to be similar to that in Spirit. So that will be noise brown struct. And it will have a field called previous sample. And that's it, actually. It's a data structure with a single field. Kind of underwhelming, but it is what it is. Could be even a box, I think. Right, so we need to create a function to initialize this brown noise generation kind of thing. So we'll have a noise brown new. Yeah, I think that's how I was calling things. And then I am going to create one of these data structures. Well, why don't I just go to the part that creates a filter? There we go. The creation of the filter is going to be similar to the creation of the noise generation. So I will say that this is noise, and then noise is equal to that data structure, an instance of, so I'm creating a data structure, an instance of that data structure. This is like the recipe and this is the cake. Then I need to set something on that field. So I'm going to say that initially the previous sample is going to be 0. So we are going to start in the middle. And then I return that data structure. Great. Then how does that look? I think it looks okay. Yeah. And then I will do something like this. And I will also need a current sample. Now I need to get a hold of the previous sample, and so I need to fetch it out of the data structure. Just like that. And then I need to say what the current sample is going to be. It is going to be equal to the previous sample plus some random number, so it's going to go up and down by some amount. I don't know what this amount needs to be right now. In fact, I do, because I did this experiment before. But the question here is, we are going to go up and down a random amount, but what is the most that we can go up and down by? Because if we could go up and down by 1, then we could go from like, or actually, if we could go up and down by 2, we could move from -1 to 1 or from 1 to -1. So it would represent essentially the same as white noise. We could go anywhere. So we want to limit this range. In other words, the particle floating on water, isn't that amazing how these relationships arise? A particle floating on water can move only by a certain amount. It cannot teleport to the other side of the ocean. So we need to limit this movement. So we are going to say that it is a random number times an amount, and I will have, I'll call this variable hack, because it's a hack. We'll need to fix this. So that's the amount, and I want, again, to subtract by half of the amount, because I want this random number to be either positive or negative. I want it to be either going up or going down. So I'm going to divide by half of the hack, because again, think of the ranges. This goes between 0 and 1. So this is going to go between 0 and hack, and this is going to go between minus half hack up to half of hack. Great. So just by doing this, it could be the case that this current sample is going above 1 or below -1. And we want to make it be in this range. Now, there are several ways of fixing this. I could use some min and max, and then I could limit the range. I could essentially clip the samples, but clipping seems too harsh. So what I'm going to do instead is I'm going to fold them back into the range. I'm going to do it like this. So if the current sample is above 1, I'm going to say that the current sample is equal to, so remember, this is a number that is like 1.1. I want it to be something like 0.9. See, if it's going 0.1 above, I want it to be 0.1 below. That's kind of a distortion kind of effect. It's called wave folding, I think. It's just a simple way of making the thing more organic, not clipping, and at the same time just having it be in the range. So how do I go from 1.1 to 0.9? Well, it's 2 minus the current sample, isn't it? 2 minus 1.1 is going to be 0.9. So that's that. But of course, I also need to do the opposite. I need to do, if it's less than -1, then the current sample is, well, think about it this way. It's like minus 1.1, and we want it to be at minus 0.9. So we can say -2 minus 1.1, that's plus 1.1. So -2 plus 1.1 is minus 0.9. So we achieved our goal. So with that, we can remember this for later, because next time we call this function, we need to remember that this was the current sample. And then I'm going to return the current sample. Now, it is kind of silly because this expression already returns current sample, so this is not strictly necessary to make things work. It is what it is. I'm going to put this line here for readability. I think it reads better that way. Great. So now there is the issue of setting this hack variable, but I'll leave that to future self. I will get to that in a moment. Let's go to the place where we expect to generate brown noise. And I'm going to say that this is using now the brown noise generator. Of course, I will need to create a noise brown kind of thing. I need to allocate this. So let me move up to the init block. And in there, I'm going to find a good place to put this. It's probably going to be after the tests. But because this is the first page, I'm going to put it before the delay line. So this is the last of the tests. And then this is the beginning of us actually doing like a delay and RMS and filters and so forth. So, I should have this in a namespace, shouldn't I? So let me grab another one of these windows, put it there, and find where we are using the brown noise. So this is not just noise brown, this is instance noise brown. So I have this new naming convention where I prefix all variables in my JS effects, all of them, with the place where they occur. So if they only occur in the sample block, I say sample dot, but if they occur in multiple blocks, like it is the case here, I am going to initialize this in the init block, but I'm going to use it in the sample block. So this is instance, because it is for the whole plugin instance. So that is equal to that. Yeah, and I need all my memory allocation to happen in the init block. That's why I have it like this. So this is me creating an instance of some brown noise, and this is me using that instance. And it's so nice, right? Because from the user's perspective, it's almost the same as white noise. It's not that bad. Great. So now let's actually see if this works. But first, let me catch up with chat, because I realized that you are talking and I haven't caught up to that. Let's see. I'm watching 2 streams at the same time and not understanding either. Great to have half of your brain. Noise, that's all I play. Yes, noise is the source of everything. There is this new Fab Filter effect called Volcano, and Dan Worrell did this video for promoting it, and he does a full drum kit just using white noise. Cool stuff. When you have the time, could you walk me through local functions? Do you mean local functions in Reaper JS effects or in Reaper scripts in Lua? Because local functions are a thing in Lua, but they are not a thing in JS effects. In JS effects, all functions are global, in the sense that all functions are visible from anywhere in the program. There is, however, this thing that I use very often that is this local thing, and it's not a local function. It is just local variables within a function. So, for instance, I have I. That's a very common name. In the context of a DFT, I is an index that I loop over. And that was from the formulas we used in the DFT. But I could be something entirely different in some other context. So all the functions have this opportunity to define some variables that are local and only exist in the function body. So that's what's up with this. But this doesn't make the function local. It's just local variables in the function. Different thing. He covered it on my channel once. Basic local variables inside a function can be accessed or referenced outside functions. There you go. So what's instance then? Oh yeah, so there are 2 things to talk about in terms of instance. One is this notion of instance. That is, I have a plugin, not a function. Forget about functions. I have a plugin and I want to have some variables that exist in multiple blocks, like in the sample block, as well as in the GFX block, as well as in the init block. So I am, by convention, calling these variables instance dot. So I know that it's a variable available in the whole plugin instance. So that's my use of instance. Now there is another use of instance, which is, remember how I'm avoiding on purpose the so-called pseudo objects? Well, I am avoiding pseudo objects for all the reasons I already explained to death in this channel, but many people are using pseudo objects for the main reason that it's faster than what I'm doing. But if you're using pseudo objects, then you can make these pseudo methods or pseudo functions that have instance variables like hello. And then if you're calling this function, you would do something like my pseudo object dot and then the name of the function, like this. And for all effects and purposes, these variables work just the same. So I would need to put some parameters here and there and there, and the local variables work just the same. But I could have somewhere else a line that reads my pseudo object.hello is equal to 34. And then within this function body, well, it's no longer really a function, it's more like a method in this case, If you know object-oriented programming, this is going to make a little bit of sense for you. But if you don't know object-oriented programming, don't worry about the difference between functions and methods. The point here being that this hello variable is now equal to 34 because my pseudo object had 34 in that slot. I'm avoiding pseudo objects because they are not so flexible, but also because they can be kind of confusing. So I think of this dot as just namespacing and I'm not using all the pseudo objects facilities that actually motivated the dot to begin with. Okay, so I hope that that covers that. And then an instance of a function is one time that it's referenced, like you have an EQ, but you can have many instances of it. Yes, that's another use of instance. So see, it's a loaded term. Instance can be many things. Sometimes when I say instance, I mean I have a recipe for the cake and I want to make a cake. So I have a recipe of how to create a data structure to remember the previous sample of a brown noise generator. So I have a recipe for that data structure. When I want to create an instance of that data structure, see, I just used the word instance. So you can do a function to round up a number, but I use multiple times in my script. That's right. So the local variable name can be used in other functions and not interfere. Exactly. You can have the same variable name, like in my example, the letter I, can be a variable in many function calls. Some of these function calls may be happening in the sample block or the GFX block, so they run at exactly the same time, and they are different variables. Instance function is like calling a DLL. What? Yeah, a DLL is a dynamic library on Windows, and I don't know how to answer that. I'm sorry, but I don't know how to react to that. Right, okay, so we have all this brown noise stuff. Let me commit what I have and we'll check it out. And we still have to deal with hack, right? That's why I'm committing, because we'll need to change numbers here and there. So let's recap what we did. So in the demonstration effect, to use brown noise, in the init block, you create an instance of the brown noise data structure, a data structure that will remember previous samples or previous sample. And then to generate noise, you just say, generate some brown noise, and you need to give the instance, because that's where the previous sample will be stored. So that's all there is to using white noise. To create white noise, well, I had to define a data structure to remember the previous sample. I have to give you a way of creating an instance of this data structure. See, used the word instance again. And then I have to actually get a hold of the previous sample, and then I move it up or down by some amount. Then I fold the wave back into the range that we like, remember it for later, and return it. And also, I initialize the white noise stuff. And I put this white noise stuff data structure creation in one place because I know that I will need a data structure for pink noise as well. Right, so let's try this out. Let's go to Reaper. Let's make sure that the master is muted. It is. And then let's drop this effect in there and play around. Or actually, before I do that, we know that the hack is being used. The hack variable is being used, but it has not been defined. So its value is 0, because if you use a variable in JSFX and you don't define it, it has a value of 0. So we are adding a random amount that is 0, and the previous sample starts with 0, so it's never gonna get out of 0. So let's have a slider real quick, a slider that we will remove, but we are going to have slider 15. It's going to be called hack. It's going to start at 0, and then it's going to go from -1, no, not -1, right? Let's think about how hack is being used. We are already taking into account that values need to be positive or negative. So it needs to go between 0 and 1, or maybe even between 0 and 2. 0 represents here no movement at all. A particle is in water, but it's never moving. And 2 is the particle can move anywhere. Doesn't really make sense, but... And we want this to be fine-grained, so I'm going to give you a lot of steps to go through. I'm going to call this hack. So now we have a slider to play with. And then we can find a value that will make things work. Right, so right now we are generating white noise. Let's move on to brown noise and look at it in the spectrum analyzer. Yeah, it's not generating any sound because we are with a hack of 0. With a hack of 0, the particle is not moving up and down. It's not moving anywhere. But let's increase this value, and then you can start to see some movement here on the spectrum analyzer. Am I right? And we have a tilt of 6 dB. Great. So now our job is to find some value that will make this a straight line. And I don't think I can find a value like that, can I? But look at this meter going. We are making this a very small number, right? So because this number is very small, the particle can only go up and down by a very small margin. Let me bring the gain down. So you can see that the particle is moving. It's moving so slowly that it's like an LFO, I guess. It's moving super, super slowly. And we can see the movement of the particle on water here. It kind of resembles something on water moving around. So it is so slow that it only produces a DC offset, which shows up as this. Yeah, that value is too small. And we know that a value of like 0.75 is already too much because it is not producing. Or is it? Hang on, what is it? What is going on here? I'm looking at this the wrong way, aren't I? I'm looking at the spectrum of mid versus side. No, I know that I'm producing different brown noises for every channel, so I'm going to just look at one of them. And look at this. And there is a tilt here. So there you go, that's better. That's more or less what I wanted. And as I increase this number, okay, that's great. So if I increase this number and make it 2, now I made the particle be able to teleport. It's moving all over the plane. So it is essentially just white noise. See, the same slope as we had before, and if I turn off the tilt, it's a straight line. So this is white noise. Now, for a 6 dB kind of slope, I can move the hack to lower and try to find a place where the line becomes straight. Yeah, I don't want to play with values bigger than, I'm going to say 0.2, okay? So let me go back into the effect and change this to be 0.2. And the 0, the leading 0 is actually optional. Did you know that? I always put it because I think it looks better, but it's actually optional. In C, it's like that too. Right. And oh, and also, so we're not that far, right? We are not that far from a straight line with the 6 dB tilt. And look at the spectrum. Look at the oscilloscope. It is still random, of course. It's still going up and down like crazy. But look at the shape. It is resembling the thing on the paper. Much more than the white noise, of course. So it's starting to look like the thing on the paper. Let's hold for a moment. And maybe dive in. See? This is what brown noise looks like. It's a random walk still, but it's limited in range, and sometimes it's gonna go below. And then if you go Sometimes it's above, sometimes it's below, but it's in that range. And in effect, what we are doing is we are limiting the travel of the samples. A sample cannot be too far from the previous one. So we are cutting the high frequency content and we are keeping more of the low frequency content. Very cool, right? And we are not effectively doing any kind of filtering on white noise. We are producing brown noise from the physics of what brown noise is. Cool. I find that fascinating. I actually enjoyed a lot reading this article. I'm going to put it in the link. I'm going to put the link in the description below. I didn't do that before the stream. I didn't want to spoil. Right. So now we have a better range for hack. Let's go back in there and fine tune something that works. And I have to do this because this article is from 1977 or 1978. Back then, they didn't have this concept of digital samples going from -1 to 1. So this paper doesn't really have any recipe in terms of what this value needs to be. It is, in fact, even not necessarily talking about noise, it's talking about generational composition, and then that would be the pattern you would choose to pick nodes. Yeah, it's a very fun article. I'm not going to dive too deep into that. So let's drop the effect back into the track. And then go into brown noise. The tilt in the spectrum analyzer is still the same. It's 6 dB, and let's play around with hack. That's too low for me to read, so let me bring it up. If I change the hack, it also makes the sound louder, which is not exactly what I was expecting. Let me think about it. Yeah, it doesn't really make a lot of oh, yeah, it does make a lot of sense. Because I'm making the particle vary more, so there is more movement on the speaker cone, which makes everything louder. But if I go too loud, then this is not a 6 dB slope anymore. But I think I find a value that 0.1 may work well for us. And maybe there is a prescribed value for this, but I don't know. And just by reading that article, I cannot tell. Let's go to 0.8. I think that's fairly acceptable, maybe 0.7. Yeah, I think that this is pretty acceptable. Let's go with 0.05. And I know, it's a hack. It's in the name. So I guess I will have a local variable just to document this hack. I'll call it magic number. No, I will not call it magic number. Travel amount. And travel amount is equal to what was our value, 0.05. And I'll say that this was calibrated by hand, looking at the sound in a 6 dB tilt spectrum analyzer. And I should see changes in both files. There you go. Now let's load this again just to make sure that everything still makes sense, and remove the demonstration thing, re-add the demonstration thing, go to brown. Is there any other occurrence of hack in here? No. Great. Okay. Go to brown and increase the volume, and there you have it. That's brown noise at -13. Looks about right. Let's hear this white noise, this brown noise. you notice there was no change in volume? It's still at -12, but man, brown noise is a lot nicer to hear. We had a brown noise machine sitting next to us while the baby slept for 1 year and 2 months at this point. At this point, the baby turned off the machine. He was like, I have enough brown noise for my entire life. I'm gonna download this episode and watch it again. Hang on, if you use the random times value on a regular audio signal, you would add a bit of noise in a novel way. Might sound cool. I'm guessing a real high frequency sheen. What exactly are you saying? You would multiply a sound wave and you would multiply a random value. What would that amount to? Well, I think it amounts to white noise, because yeah, I think it amounts to white noise. If you multiply by a random value, it amounts to white noise. If you add a small random value, you're just mixing in white noise into the signal. But if you multiply, I think you end up with white noise, right? A random number times something like a signal is still a random number. Yeah, I don't know. We could test that, but I don't know. Because our ears are more sensitive to high end, so the same peak meter reading won't translate to equal amount of perceived sound. More about that when we get to implement LUFS, but not today. And that would be a bit like data moshing. That add a random value between samples. I don't know what that would do. Like the values are multiplied randomly. Yeah, I don't know what that would sound like, but you can go grab my library and try it for yourself, because now we have brown noise. And I was thinking we could do pink noise today, but it seems like I was over ambitious. So I want to wrap this up, and I'm going to recap the main points. White noise is... Yeah, there is actually one more thing that I want to say about brown noise. Before I recap, I just want to make sure that I'm not forgetting anything. So yeah, one more thing that I think is important to say about brown noise. It's sometimes called 1/f². And that for me was like, what? What is 1/f²? Yeah, so you know what? I'm gonna leave this for when we talk about pink noise, because pink noise has an even better notion of what this is, because pink noise is 1/f noise. Where does it say that? I don't know, but it's, yeah, 1/f fluctuation. This is 1/f is pink noise. And I will explain why it is called 1/f. Has to do with energy and power, and it is a lot of fun. If you do what I did, if you do what you said you would, Bo, and you download and rewatch this episode, you're going to realize that I never mentioned energy or power in this whole episode, because it is an incorrect term. If you watch my previous streams, in many cases, I will say that this has an equal amount of energy across the spectrum or an equal amount of power across the spectrum, and those are wrong. I'll get to that when we talk about pink noise. And yeah, so to recap, white noise has slices of all the frequencies because it jumps over randomly, so some samples will be closer together and others will be further apart. Brown noise has this slope of six dB, and we were able to reproduce something like this, not by filtering white noise, but by doing a random walk with the samples that kind of looks like this. And we calibrated this to be in the right range so that it would sound like 1/f² or brown noise. Brown noise does not correspond to a color. Brown noise is a person. And yeah, I think that is pretty much it for this episode. And in terms of code, we implemented the whole thing. We even implemented something that I actually may want to implement separately, which is wave folding, because it's a type of distortion for like guitars. Could be useful somewhere. So we might extract this somewhere. So let's catch up with what you are all saying, and I will give you the schedule. Okay. Explain pink noise briefly. Oh no, pink noise is the best of all. It's great. I will do a whole episode just about that. Has data moshing been done in audio? Absolutely. I still use it. I need to know what that is now. Never heard of this. Yeah, I'll look it up. Nothing specific, but you can mosh data in. You can also export the audio as text file, change stuff, import an audio. Okay, I'll look into that. Seems interesting. So here's the schedule. On Monday, I'm going to be on IDGQD Sound, and we are going to continue working on our ping pong delay, which is a ping pong ball dropping. Then on Tuesday, I am going to get to my Arduino stuff because I bought the parts I needed. So we are going to finish our MIDI pedals and expression pedal, all using an Arduino. We're going to be continually building our own MIDI controller. In video, you can data mosh, like you can change all P frames in a video to B frames. I know what P frames are and I know what B frames are, but I don't know what you mean by that. Yeah, so on Tuesday, we'll be back to Arduino. On Wednesday, we are going to continue our orchestration. And on Thursday, I will get back and talk about pink noise. It's going to be a lot of fun. All right. Thank you all for being here. I hope you have a great weekend, and I am going to sign off now. Thank you for being here. Bye.